Today I would like to discuss the oxidative addition reaction. Dear students, myself Dr. Digna Varghese. Oxidative addition reaction, which is also known as OXAD reaction, one of the most important classes of reactions in organometallic chemistry is oxidative addition. An initiating step or key step in a catalytic process and involves the formation of bonding between metal and organic or inorganic substrates. A coordinatively unsaturated complex in a relatively low oxidation state undergoes a formal oxidation by 2 units, and at the same time it increases its coordination number by 2. Generalized form of oxidative addition reaction is when a complex reacts with organic or an inorganic substrate, undergo oxidative addition reaction, and here the metal with N plus oxidation state and coordination number is 4 here. After oxidative addition reaction, metal increases its oxidation number by 2 and coordination number is also increased by 2, 4 to 6 and N plus 2, N plus 2. This is generally known as an oxidative addition reaction, which is an important step in homogeneous catalytic process. There are several pathways by which one ligand may replace another in a complex, including nucleophilic substitution, electrophilic substitution, and oxidative addition followed by reductive elimination reactions. You would have seen several oxidation addition reactions, often in catalytic cycles. These cycles are taken advantage in an industrial processes to efficiently generate materials. For example, acetic acid can be produced by Monsanto and Catawba process, and in this catalytic cycle, oxidative addition reaction is the first step. And in the case of ammonia, by Haber process, and in the case of sulfuric acid, the manufacturing process is from contact process, and many other useful substances we use today can be synthesized with these type of reactions. A large number of molecules add oxidatively to a metal atom, including the alkyl and aryl halides, dihydrogen, and simple hydrocarbons. In general, the addition of any molecule XY to a metal atom, where both X and Y are more electronegative than the metal, can be classed as oxidative addition reaction. Thus, the reaction of a metal with an acid such as HCl is an oxidative addition reaction. Oxidative addition reactions are not restricted to D-block metals. The reaction of magnesium to form Grignard reagents is an oxidative addition reaction. The bonding of dihydrogen to a metal atom, if we noted that the oxidation number on the metal atom increased by 2 when the dihydrogen reacted to give a dihydride, here representing a general example, that is MnOx plus hydrogen giving Mn oxidation state increased by 2 and hydrogen add to this. If the metal is electron rich and is a sufficiently low oxidation state, the pi back donation results in homolytic cleavage of hydrogen bond, and the 2 hydrogen atoms are formally reduced to H with concomitant oxidation of the metal. This process is known as oxidative addition by adding dihydrogen molecule to the metal atom. In this transformation of the dihydrogen molecule to a dihydride is an example of oxidative addition. That is, the metal is oxidized by 2 units by this reaction and the dihydrogen is reduced to hydride ion. A dihydrogen molecule is treated as a neutral 2-electron donor. Thus, the transformation of the dihydrogen into the two hydrides requires the formal charge on the metal atom to increase by 2 units. So, addition of dihydrogen molecule to the metal atom is an example of oxidative addition reaction. Oxidative addition of hydrogen is exemplified with the so-called the Vasca's compound, that is having the general formula IRClCO ppH3 twice. This is Vasca's compound. It is a iridium based complex, and in this compound, the Vasca compound reacts with hydrogen, forming an oxidative addition of hydrogen occurs. The formal oxidation state of iridium increases from +1 here, that is increases to +3 after addition of hydrogen, and the coordination number is 4 here, and which is increased by oxidative addition by 2 units, that is in this compound coordination number of iridium is 6. And here the ball and stick models of Vasca's compound, and here after addition of hydrogen molecule to form the coordination number 6 compound. In the product, the two hydrogen atoms are regarded as hydrido-hydrogen atoms with the metal, and the hydrido-hydrogen ligands increases its oxidation number by 2 units, and the coordination number of iridium metal in this compound is 6. So, this is an example of oxidative addition reaction. Here illustrating some reactions for oxidative addition reactions. The oxidative addition reaction shows the oxidation of platinum 2 to platinum 4 with simultaneous expansion of the coordination number from 4 to 6. In this platinum complex, there is methyl ligand, chloride ligand, and a substituted phenyl type phosphine-like ligands, and its coordination number of platinum in this compound is 4, and its oxidation state is 2. After addition, oxidative addition of chlorine, and giving the coordination number increased by 2 units, that is coordination number of platinum in this compound is 6, and its oxidation number is increased by 2 units to 4. So it is an oxidative addition reaction. Another example is when Wilkinson's catalyst, the hydrogenation reaction, we are using Wilkinson's catalyst, and here the first step is addition of hydrogen to the catalyst is formed by the elimination of a triphenylphosphine group to form hydrido complex, and it is an oxidative addition reaction. Here the coordination number increased by 1 unit, and the oxidation number increased by 2 units. And another example for oxidative addition for the complex IRClCO ppH3 twice, that is Vasca's compound, that is we are already seen, and it also increases its coordination number and oxidation state by 2. Here also representing some other examples for oxidative addition reactions. In this reaction, the methyl bromide is added to the iridium compound, that is Vasca's complex, and after the addition, both coordination number and oxidation number increased by 2 units. And this is another reaction. We are adding to this rhodium complex an alkene, and it is coordinatively unsaturated, and its coordination number increased by 1 unit to this, and oxidation number is also increased. And in the case of manganese pentacarbonyl, methyl bromide is added to this, and the oxidation state and the coordination number also increase. And here the hydrogen iodide is added to the Vasca's compound, and by after this oxidative addition by hydrogen iodide to this molecule, increased its oxidation number by 2 and coordination number by 2. Show that the reaction is an example, and this reaction is an example of oxidative addition reaction. In order to identify the oxidative addition reaction, we need to establish the valence electron count and the oxidation state of both the starting material and the product. The 4-coordinate rhodium complex starting material contains an 1-alkenyl ligand as 3-phosphenyl ligands neutral. It is therefore rhodium-116 electron species. To this, a methyl alkenyl species is added to this compound, and to this the 6-coordinate octahedral product contains 2 1-alkenyl ligands and a hydride ligand here, the 3 neutral phosphine ligands. It is therefore an 18 electron rhodium-3 species. So, increase in both coordination number and oxidation state in this compound or the product after the reaction. So, it is an oxidative addition reaction. Conditions for oxidative addition reaction. In view of the extensive applications of oxide reaction in catalysis, some of their essential features are indicated as follows. First one is low oxidation state of metal. Metal should be low oxidation, in a low oxidation state, that is electron rich metal. Oxidation of the metal is easier for electron rich systems than for the electron poor ones. Hence the oxidative addition is more likely for low valent metals. Second essential feature for the oxidative addition reaction is coordinative unsaturation. The OXAD reaction are generally accompanied by an increase in the coordination number of the central atom. Therefore, the precursor complex should be coordinatively unsaturated. That is, it has a vacant space to accommodate ligand further. The coordinative unsaturation can be achieved either by the generation of a vacant coordination site. We can generate a vacant coordination site for the complex, or by the other method, by the ability of the complex to exist to different coordination numbers. Where different metals has different coordination numbers, and if the metal with to exist to a different coordination number, it can exist in both +6 oxidation coordination number 4 and coordination number 6, or it can exist like coordination number 4 to 5, etc. For coordinatively unsaturated complexes like D8 species in solution, coordinating solvent molecules occupying the vacant sites could be displaced by reacting molecules. Here we can see the coordination number 4 of the rhodium-1 complex. The solvent can be replaced by one of the ligand, and it is added to the oxidative addition reaction by hydrogen molecule, and it is replaced by the solvent molecules by hydrogen. So the vacancy can be created by replacing the ligand with the solvent molecules, and which can be replaced by the coming ligand. These coordinated solvent molecules should not be too tightly bound to the metal atom. Otherwise, if they are tightly binding or bounded to the metal atom, they effectively poison the catalyst, which is unable to present a vacant coordination site for the incoming substrate molecule, that we have already seen in the case of Wilkinson catalyst. Another method for the creation of vacancy sites. In a 5 coordinated complexes, the vacant sites formed by the dissociation of one or more ligands either by thermally or photochemically. In the case of iron pentacarbonyl, which undergo photolysis and forming the replacement of one carbonyl ligand from the iron pentacarbonyl, and another method by thermally. Here the rhodium based catalyst, it is by the action of heat, it replaces one of the triphenyl phosphine ligand and forming a vacancy here. Another method is by the use of ligands with a high trans effect to create a vacancy sites. In this method, for example, platinum tetrachloride treated with alkene in presence of by the elimination of one chlorine ligand, this alkene is coordinated to the metal atom. Here, by the use of a high trans effect ligand which can replace one of the ligand in the complex, so we can create vacancy in the complex by removing one of the ligand by a solvent molecule, or by we can dissociate ligand by either by photochemically or by thermally, or by the use of ligands with a high trans effect. These methods can be used to create vacancy or for the coordinative unsaturation in a complex for oxidative addition reaction. A vacant coordination sites must be available for oxidative addition reactions. A 6-coordinate complex is not a good candidate for oxidative addition reaction unless it loses ligands during the course of the reaction, making available a site for interaction. So there should be a coordinative unsaturation in a complex to perform oxidative addition reaction. Therefore, there should be suitable orbitals be available for bond formation. An 18-electron complex contain Ml4 type. If addition of XY would require the use of antibonding orbitals, which of course is not energetically favorable reaction. So, always 16-electron complex with coordination number 4 can undergo easily oxidative addition reaction without any creation of vacant sites or by using any antibonding orbitals. For example, iron tetracarbonyl, it has only 4 ligands, but addition of XY would require the use of antibonding orbitals, which of course is not an energetically favorable reaction. So, oxidative addition reaction results 2 more ligands bound to the metal with an increase in the total electron count at the metal of 2. Thus, oxidative reactions normally require a coordinatively unsaturated metal center, that is in 16-electron platinum 2 complexes like square planar complexes. So, always used as catalyst in several reactions with square planar complexes rather than octahedral or other geometry, because it has coordinative unsaturation and also the vacant available suitable orbitals for available bond formation. The oxidative addition reaction generally facilitated by the availability of the vacant coordination site on the metal complex in solution, that is in the case of homogeneous catalysis, or a metal surface, that is in the case of heterogeneous catalysis. The coordinative unsaturation may also arise from the dissociation of loosely held solvent molecules, giving rise to potentially vacant site. This can be happens in the case of Wilkinson catalyst. First, we can replace it by a solvent molecules with the triphenyl phosphine ligand, then undergo oxidative addition reaction with this catalyst. Metal complexes with the 18 electrons in the valence shell are coordinatively unsaturated irrespective of the coordination number and therefore catalytically ineffective. If the metal complex has 18 electrons, that is coordinatively saturated complex. If the coordination number is not increased to 6 or 8 or any other coordination number. If it is 4 with 18 electrons, that is catalytically ineffective. Coordinative unsaturation is generally gated by therefore 18 electron rule or by effective atomic number rule, that is EAN rule. For example, coordinatively saturated complexes IRCl H2PPH3, that is a D6 compound, and FeCO5 D8 compound. In this case 18 electron, it is an 18 electron complexes. Coordinatively unsaturated complexes like 16 electron Wilkinson catalyst. Here a table shows. This table indicates the number of ligands required to saturate coordinatively the respective metal ions, and consequently the corresponding complexes with lesser number of ligands would be coordinatively unsaturated. For the electronic configuration D6, the saturated coordination number is 6. For example, rhodium 3+, Ir3+, CO3+, Ru4+, platinum 4+, molybdenum 0. This can be used as the metal complexes can be used as the saturated compound with the D6 configuration. So this number is 6 is required for the saturated coordination number, and lesser number of ligands, if it is contains 4, it will be coordinatively unsaturated. D8 electronic configuration with the saturated coordination number is 5. If it is 4, it is coordinatively unsaturated. The metal complexes shown, metal ions shown here are examples of D8 electronic configuration. D10 configuration, the saturated coordination number is 4, and the metal is nickel 0, PD 0, and platinum 0. Another condition for the oxidative addition reaction is the nature of the metal ion. For example, there are many indications that the lighter metal in a given subgroup are less basic or nucleophilic than the heavier elements. We considering the cobalt group in a transition series, that is cobalt, rhodium, iridium are present in the subgroup, and we see the heavier element iridium complex, which reacts completely and irreversibly with the methyl iodide, and the reaction is reversible, not in the reversible mode, it is complete reaction with the methyl iodide. And when the same complex with rhodium metal, which is a lighter element compared to iridium, so it is less basic or nucleophilic than the iridium one, so it is undergo a reversible reaction with the methyl iodide. But there are some few exceptions. The general tendency to undergo oxidative addition reaction. Here we can see that the ease of oxidation, that is usually D8 to D6 with the formal loss of 2 electrons, the relative stability of the coordination number 4 compared to 5 or 6, and the strength of new bonds created mx and my relative to the bond broken xy, all must be considered. Here we can see from a subgroup iron group, cobalt group and nickel group with the same oxidation state, increasing tendency for OXAD reaction is with the heavier elements, and in the same period increasing tendency for OXAD reaction is in this direction. Therefore, the ease of oxidation increases from top to bottom within a triad, that is cobalt less than rhodium less than iridium. So iridium is the most easier element in this group to undergo oxidative addition reaction, and the tendency toward 5 coordination decreases from left to right across a transition series, that is osmium 0 is greater than iridium, and for platinum 2. Electronic nature of the ancillary ligands. Ancillary ligands means which are defined as those ligands that provide the appropriate steric and electronic environment around the central element but remain innocent in any transformation that the compound undergoes. In contrast, the reactive ligands are those groups that undergo changes. Spectator ligands are sometimes referred to as ancillary ligands, not participating in the reaction. The presence of ancillary ligands which enhance the electron density around the metal atom in a complex also influences the course of the reactions. For example, in the Wilkinson's catalyst undergo a fissile oxidative addition reactions. Here the HClCO ppH3 twice is much less active for oxidative addition reaction. Here one of the triphenyl phosphine replaces by CO ligand, that is increases the electron density around the metal atom, and that is much less active for oxidative addition reactions. A steric factor is another parameter to be considered. The observed order of hydrogenation activity in Wilkinson catalyst, that is triphenyl phosphine with a high steric effect, is greater than triphenyl phosphine and the fluorosubstituted triphenyl phosphine. Here with electron negative element substituted phenyl group, which is a electron attracting. So this ligand decreases the electron density around the metal, that less active for oxidative addition reaction, and the steric effect and also the electron releasing group also increases. This type of ligands is much easier for oxidative addition reactions when attached to the metal atom. Important condition for the oxidative addition reaction is nature of the addendum, that is oxidative addition reactions involving a cleavage of carbon-carbon bond would be obviously less feasible. Such cleavage can be brought about when sterically crowded addendums such as C2PH6 molecule, for example nickel metal complex, reacts with C2PH6 molecule. It will undergo a cleavage carbon-carbon bond here, and nickel is added to this and elimination of NL ligand. Oxidative addition reactions involving a cleavage of carbon-carbon bond would be obviously less feasible, but such cleavage can be brought about when sterically crowded addendums such as C2PH6 molecule. So the nature of the addendum can also influences the oxidative addition reaction. Another important criteria for the oxidative addition reaction is its stereochemistry and the mechanism through which the reaction proceeds. Sometimes the product is added cis and other times it is added trans. Stereochemistry, the product is sometimes cis stereochemistry, and in other cases sometimes it may be trans. How it's added depends upon the mechanism which undergo. Mechanisms for oxidative addition reaction is that mechanisms for oxidative addition reactions vary according to the nature of the XY. Here we are representing the XY is non-polar, as in the case of hydrogen. A concerted reaction leading to a 3-centered transition state is most likely, and here the viscous compound reacts with hydrogen, undergo oxidative addition reactions with a 3 centered transition state here, and which breaks to give the oxidative addition product. A dioxygen is another nonpolar molecule, also adds reversibly to Vasquez complex, but in this case XY bond is not completely broken. The bond order of oxygen is reduced from 1, 2 to 1. Many D-block complexes have been isolated that contain a relatively stable intact hydrogen ligand. First such compound is a tungsten-based complex. Here tungsten attached to 3 CO ligands and hydrogen and a tri-isopropyl phosphine type ligands, and both hydrogen atoms in hydrogen molecules may be coordinated as ligands to the same metal atom. The complex ruthenium hydrogen, a complex like ruthenium complex, contains 6 hydrogen atoms in the inner coordination sphere, and the 2 kinds here 4 hydrogen and with 2 hydrogen here, therefore it contains 6 hydrogen atoms in the inner coordination sphere. The 2 kinds of ligand hydride atom and hydrogen molecule can be distinguished by neutron diffraction method. So these many G-block complexes with a stable, relatively stable hydrogen ligand can be identified with both spectroscopical techniques and also in the neutron diffraction methods. These are examples of oxidative addition reactions. For the non-polar molecule substituted to the metal compounds. The oxidative addition of hydrogen is a concerted reaction that we have seen already. Dihydrogen coordinates to form a bonded hydrogen ligand, and then back bonding from the metal results in a cleavage of hydrogen-hydrogen bond and the formation of cis dihydrides. For example, the 4-coordinate 16-electron rhodium-1 complex undergo oxidative addition reaction with hydrogen and forming here the hydrogen-hydrogen bond with the rhodium and cleavage of hydrogen-hydrogen bond to cis product. Other molecules such as alkanes and aryl halides are known to react in a concerted fashion, and in all these cases the 2 incoming ligands end up cis to each other. Another mechanism is if XY is an electrophilic polar molecule such as methyl iodide, the oxidative addition reactions tend to proceed by SN2 mechanism involving 2 electron transfer or via radical 1 electron transfer mechanism. Here the complex reacts with methyl iodide. It is an electrophilic polar molecule and undergo by SN2 reactions and forming a product. Here the radical mechanism by 1 electron transfer. Here it is by the 2 electron transfer. Here it is by 1 electron transfer. Other factors besides a vacant coordination site are important in determining the tendency for a complex to undergo oxidative addition reaction. Some oxidative addition reactions are not concerted and either go through radical intermediates or are the best thought of as SN2 displacement reactions. Radical oxidative addition reactions are rare and will not be discussed further here. In an SN2 oxidative addition reaction, A lone pair on the metal attacks the XY molecule, displacing Y, which subsequently bonds to the metal. Here, the methyl iodide undergo oxidative addition reactions with the iridium complex and forming SN2 oxidative addition reaction by a lone pair on the metal attacks by the S. Thank you for hearing me.